This is a video from section 1.7 in a linear algebra class. A square matrix in which all the entries off the main diagonal are 0 is called the diagonal matrix. Let's take a look at some examples of diagonal matrices. Number 1. Suppose I give you the matrix 2, 0, 0, 4. The entries along the main diagonal are 2 and 4. But do you notice how the entries off the main diagonal are all 0? And so this is an example of a diagonal matrix. Number 2. Suppose I give you the matrix 1, 0, 0, 0, 4, 0, 0, 0, 5. The entries along the main diagonal are 1, 4, and 5. But all the entries off the main diagonal are all 0. And so here's another example of a diagonal matrix. And let's take a look at a third example. Suppose I give you the matrix 1, 0, 0, 0, 4, 0, 0, 0, 0. The entries along the main diagonal are 1, 4, and 0, right? Now, I never said an entry along the main diagonal can't be 0. It very well can be 0. But what we care about are the entries off the main diagonal. And if you notice, the entries off the main diagonal are all 0. And so example 3 is another example of a diagonal matrix. The following matrix is not a diagonal matrix. Suppose I give you the matrix 0, 0, 1, 0, 2, 0, 3, 0, 0. This is not a diagonal matrix. Why? If we circle the entries or highlight the entries along the main diagonal, we get 0, 2, and 0, right? But if we look at the entries off the main diagonal, they're not all 0. So notice here's 3 and here's 1. 3 and 1 are entries that are not equal to 0 and they're off the main diagonal. So this is not a diagonal matrix. I hope that's okay. Now, why do we care about diagonal matrices? A diagonal matrix is invertible if and only if all of its diagonal entries are not 0. For example, let D equal the matrix 2, 0, 0, 0, 3, 0, 0, 0, 4. Notice that all the entries along the main diagonal are not 0. So notice we have a 2, we have a 3, and we have a 4. None of these entries are 0. And so by the previous result, we can tell that D is invertible. We can tell that this 3 by 3 matrix is invertible immediately. And not only can we tell that it's invertible, finding the inverse is very straightforward. So if we want the inverse of D, here's what we do. Now, if we take the reciprocal of 2, we get a half. And so that's in the first spot. And so we're looking at the entries along the main diagonal of D inverse. The reciprocal of 3 is 1/3. And the reciprocal of 4 is 1/4. And then it turns out all the entries off that main diagonal of D inverse will all be 0. So I put a 0 here in here, a 0 here, a 0 here, a 0 here, and a 0 here. So let me say that again. To get the entries along the main diagonal of D inverse, we took the reciprocal of 2, the reciprocal of 3, and the reciprocal of 4. And then all the other entries off that main diagonal are all 0, or they remain 0. And that's how we get D inverse. So to kind of give you an idea, so like, for example, if D was just a 2 by 2 matrix, suppose we had 4, 0, 0, 5. And then I wanted D inverse. Now look, the reciprocal of 4 is 1/4. The reciprocal of 5 is 1/5. And then I just put zeros everywhere else. And so getting the inverse is immediate. Okay? So that's how we do D inverse. Now, if D was the matrix 4, 0, 0, 0, 3, 0, 0, 0, 2, and then I want to find D to the 4th, that's also straightforward. So the way that works is I'm going to take the first entry 4 and raise it to the 4th power to get 4 to the 4th. And we're looking at the entries along the main diagonal. And then what I do is I take the entry 3 and raise it to the 4th to get 3 to the 4th. So now I have 4 to the 4th here and 3 to the 4th here. So we're looking at the entries along the main diagonal of D to the 4th. Because remember, if D is a diagonal matrix, D to the 4th will turn out to be a diagonal matrix as well. And then I'm going to take 2 and raise it to the 4th to get 2 to the 4th. And then every entry off the main diagonal will just be 0. And then when I'm finished, this is equal to the matrix 256, 0, 0, 0, 81, 0, 0, 0, 16. And I'm done immediately. So taking a diagonal matrix and raising it to a power is very quick work. Okay? So to kind of give you another quick example here. If D is the matrix, -1, 0, 0, 0, 5, 0, 0, 0, 2. Okay? And I want D to the 3rd. And so all I have to do is take this entry and -1 and raise it to the 3rd. That's going to give me -1. The rest of the entries in the first row are all 0. Then I put a 0, and then I'm going to take 5 and raise it to the 3rd. 125. And then I put a 0, and then I go 0, 0, and then I'm going to take 2 and raise it to the 3rd to get 8. So it's very, very straightforward to take a diagonal matrix and raise it to a power. You can find the inverse of a diagonal matrix, right? That's what we did here. And we can take a diagonal matrix and raise it to a power. That's what we did over here. Okay, let's keep going. To multiply a matrix A on the left by a diagonal matrix D, multiply the rows of A by the successive diagonal entries of D. To multiply A on the right by D, multiply successive columns of A by the successive diagonal entries of D. So let's take a look at that. Suppose A is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And D is the matrix 2, 0, 0, 0, 4, 0, 0, 0, 2. Okay. So what I want to do is I want to take a look at the matrix DA. So D is on the left side of A for this one. So we're going to take the matrix 2, 0, 0, 0, 4, 0, 0, 0, 2. And I'm going to multiply by A. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, what's nice about this? When I take D times A, now I want the first row. Now, here's what the first row is going to look like. I'm going to take 2 and multiply it by 1. That's going to give me 2. I'm going to take 2 and I'm going to multiply it by 2. That's going to give me 4. I'm going to take 2 and I'm going to multiply it by 3. That's going to give me 6. What do I do next? To get the second row of D times A, I'm going to take 4 and I'm going to multiply it by 4. 16. I'm going to take 4 and I'm going to multiply it by 5. 20. I'm going to take 4, multiply by 6. I get 24. That's row 2. To get row 3, I'm going to take 2 times 7, 14. 2 times 8, 16. 2 times 9, 18. And we just found DA. Now, suppose I want AD. It's a little bit different, right? So I'm going to take 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to multiply by, now, this is 2, 0, 0, 0, 4, 0, 0, 0, 2. Now, what do we do there? So, I want the entry in the first row, first column of AD. And so, I'm going to take 1 multiplied by 2. So, that's going to be a 2. Okay? And then, if I want the entry in the first row, second column, I'm going to take 2 and multiply it by 4. 8. If I want the entry in the first row, third column, I take 3. I'm going to multiply it by 2. 6. Now, we can go this way, right? Now, if we go to the second row, all right, I'm going to take 4 times 2 again, 8. 5 times 4, 20. 6 times 2 is 12. That's the second row. To get the third row, I'm going to take 7 times 2. So notice how every entry in the first column of A got multiplied by 2 to get the first column of AD. So let me say that again. Every entry in the first column of A got multiplied by 2 to get the first column of A times D. Then I'm going to take 8 times 4 to get 32, and then 9 times 2 to get 18. So every entry in the second column of A got multiplied by 4 to get the second column of AD. And every entry in the third column of A got multiplied by 2 to get every entry in the third column of A times D. One more time. I took every entry in the first column of A, multiplied it by 2 to get the entries in the first column of AD. I took every entry in the second column of A and multiplied it by 4 to get the entries in the second column of A times D. And then I took every entry in the third column of A, I multiplied it by 2 to get every entry in the third column of A times D. So it's really, really slick. And so multiplying any matrix by a diagonal matrix is very, very straightforward. Okay, that'll conclude this video for 1.7, and this was a discussion on diagonal matrices. Thank you.